Hi everyone! This is a talk based on the paper Branching Programs with Bounded Repetitions and Flow Formulas. I'm Anastasia Sofronova, and this is a joint work with Dmitry Sokolov. So, my talk is about proof complexity, so let me first remind you a few things about it, what proof complexity is and what does it study. Suppose we have a Boolean formula in CNF, it's a formula phi, and we would like to know if there is any efficient way to prove its unsatisfiability. Proof is something that we can check in polynomial time. Under this requirement, satisfiability would be pretty easy to prove. Indeed, we can just take a satisfying assignment and check if this assignment is really satisfying. It's not so clear what to do with unsatisfiability. So let's take a look at a few examples just to show you how could a proof system look like. Again, we have our formula phi, it is in CNF, and here is our first example of a proof system. It's a resolution. Here we have one rule. If we have two clauses of the form C of x and D or not x, we can derive from those two clauses a new clause, C or D. And in resolution, a proof of unsatisfiability of a formula phi is just a sequence of clauses where each clause is either from our original formula or it is obtained by applying this resolution rule to clauses with lesser numbers. And in the end, we have this trivially false statement, an empty clause. This system is sound and complete. It is not hard to prove this. Meaning that a formula phi has a resolution refutation if and only if it is unsatisfiable. So let's take a look at another example then. Cutting planes proof system. Here, first we rewrite our clauses as linear inequalities, and then we can do something with those linear inequalities. We can apply some rules, which are linear combination and division with rounding up. So the proof in cutting planes proof system is just, again, a sequence of inequalities where each inequality is either from the original formula or it is derived by the rules from inequalities with lesser numbers. And again, in the end, we have this trivially false statement, then 0 is greater or equal than 1. So why do we study all of this? There is this historically first motivation that if we would be able to prove that there is no polynomially bounded proof system for the language of unsatisfiable formula, meaning that for every way to prove unsatisfiability, there is a hard family of formulas which do not have polynomial size proofs. Well, that would be equivalent to NP not equal to co-NP, and then P not equal to NP would fall. That would be nice. We're very far from that. We can only prove lower bounds on certain proof systems, but this is useful in itself too, because proof systems describe various algorithms. For example, algorithms for a satisfiability problem, for example, the resolution proof system I mentioned, describes runs of DPLL algorithms. Cutting planes describes combinatorial optimization, and there are many more examples like this. Also, proof complexity is closely related to other areas of complexity theory, such as monotone computations, communication complexity, etc., etc. And in my talk, I would like to focus on the connection between proof complexity and some weak computational models. And to understand this connection, let us take a look at the following problem. It is called search phi, and here we are given an assignment to Boolean variables of this formula phi, and we would like to find a clause falsified by this assignment. So suppose we have some computational model, and in this model we are able to compute this search phi problem. Well, then the description of this computation can be viewed as a proof of unsatisfiability of our formula phi. Well, why is that? Well, if for every assignment we can find a clause falsified by it, then our formula phi surely must be unsatisfiable. There is a catch, and this catch is that we need to be able to check our computation in polynomial time. That is what we require from proofs. So if we are to view our computation as a proof, we need to check it in polynomial time. Well, if we are able to meet this requirement, then our computational model naturally induces a proof system, and lower bounds on the description of this computation of the problem search phi yields lower bound on the corresponding proof system. Well, it turns out that many classical proof systems correspond to computational models in this nice way. And as an example, I could mention tree-like resolution here, which is equivalent to decision trees for search phi. And there are a few other examples like that. Okay. So the computational model I would like to talk about today is called branching programs. The computation here is described as a graph, directed acyclic graph, and in every inner vertex we have a variable and two outgoing edges, 0 and 1, which correspond to assigning to this variable 0 or 1. In the circles of our graph, we have the results of the computation. So this branching program computes some function of Boolean variables x1, xn, and every assignment to those variables naturally induces a path in this graph. And this path leads us to the result of the computation. And note that not every path in our branching program may correspond to some assignment. Well, here you can see an example, a formula, some unsatisfiable formula phi, and a branching program that computes search phi for this formula. This is a tree here, but keep in mind that in general, our branching program can be just a directed acyclic graph. Okay, so we can compute search phi. But it's not that easy here, because if we are to consider general branching programs, then we would just have a short program for every problem search phi. And it's not clear how to check such program in polynomial time. A short program for arbitrary search phi would look somehow like this. We can just check all clauses consecutively. Like we take a clause, we ask every variable from this clause, and we check if this clause is really falsified or not. Okay, but there are important partial cases to these branching programs, and the first one is called read-once branching programs, or OneVP. Here, we require that every variable occurs at most once on every path in the program. Here, we cannot do this trick with just check all the clauses consecutively, and now we can check the program in polynomial time. And it turns out that these read-once BPs are equivalent to regular resolution, and this connection is widely used in proof complexity. In some recent results also. For example, the results about the complexity of the click problem in regular resolution, bad series, and others. And I suggest we consider a bit stronger model, which is called 1 plus KBP, in two setups, syntactic and semantic. Here, in the syntactic case, we require that on every path in our program, we have no more than k variables that occur more than once. And in the semantic case, we ask that only from the consistent paths, meaning paths that correspond to at least one assignment. So, what about those BPs? Well, good news. It is a proof system, at least in the syntactic case and for constant k. This is a generalization of the similar result from the paper by Knopf, in which this was proved only for constant with CNF. So, okay, syntactic 1 plus KBP is a proof system. This is a nice start. Let's keep it this way. Okay. What about lower bounds? Well, there are lower bounds for 1 plus KBPs, but these lower bounds were only for functions that are structurally more complex than our search 5 problem. For example, some of those hard examples are based on error correcting codes. So this has nothing to do with proof complexity. We cannot write this as a short CNF. And moreover, the technique that is used here, it actively uses the structural properties of the functions that ensure that we cannot write this as short CNF. So, if we are to deal with search phi, with something that is useful for proof complexity, we need to come up with the approach which will allow us to deal with problems with much less structural properties. So our result is the following. It is an exponential lower bound on the size of the semantic 1 plus KBP for search phi, for some formula phi, for a family of formulas. And this bound is exponential for k up to log n over log n. Let's take a look at those hard formulas then. They look like this. These are flow formulas which were introduced by Alekhnovich and Razborov. And here we take a graph G, which is a n delta alpha algebraic expander. For every h, we have a Boolean variable, and for every vertex, we have a label. This label is 0 almost for every vertex except 1, and for this one vertex, the label is 1. So, for each vertex, we write this statement in CNF. The sum of all edges that carry flow out of the vertex minus sum of all edges that carry flow in the vertex is at least the label of the vertex. What does this mean? It means that in our graph there is a source of the flow, but there are no sinks. This is impossible, so our formula is unsatisfiable, which is good. We really want a formula to be unsatisfiable. Okay, so now we take this flow formula and we modify it a little bit. How do we modify it? Let us somehow modify each of these statements for a vertex separately. So we take the statement for some vertex v, and we do the following trick, which is a modification of the trick from the paper by Alekhnovich and others. Okay, so this statement written in CNF actually has a lot of clauses, like 2 to the delta, 2 to the degree of our expander clauses. And we would like to add to every clause k extra variables with all possible signs, such that one clause becomes 2 to the k new clauses. How do we pick variables that go to the clause? First, we take all variables that occur in our formula, that correspond to edges, and they take all sets of k variables. Okay, so then we distribute these sets of k variables among our clauses for vertex somehow uniformly in such a way that every set of k variables gets its own clause. So we would like every set of k variables to be present in the statement for the vertex. Okay. So why do we need those formulas exactly? Well, first, we would like to make use of expander properties, obviously, both algebraic and combinatorial. Also, flow formulas have this nice property that we can satisfy the constraint for vertex with margin. What does this mean? So let us take a constraint for vertex V. It says that the balance of the flow in this vertex V is non-negative. Well, now I would like to say that this is not only non-negative, it is positive, and it is like the constant ratio of the degree. So if we look only at assignments that assign only variables incident to this vertex, then all the assignments with this property are very similar to each other. They all have a lot of outgoing flow, and they intersect on a lot of values of variables. So we would like to combine those assignments in some nice way, and a bit later we will see how this plays out. And the last property listed here is what we achieved by the amplification trick. And this amplification makes branching program to waste its repetition on those extra variables we added to clauses, and those variables do not really mean anything for a formula, so those repetition are just wasted on nothing. Okay. Let us now take a look at the plan of the proof. So suppose our 1 plus kbp has small size, smaller than the exponent we are aiming at. Then we would like to find a structure in the graph of the branching program, a structure called k plus 1 garland. Actually, you may have encountered this earlier in literature by the name of SL chains. We call this a garland. You can see it in the picture to the right. It is really a garland. It's very intuitive. And to find this garland, we would like to generate an exponentially big set of paths in the program. To do that, we would like to use closure, which is a technique for combinatorial expanders, and it helps to keep the formula hard under certain partial assignments. And then here we would like to use this property that we can satisfy the constraints with margin. I will explain now a bit informally how does this work here. So suppose we have found the first segment of the garland, and now we would like to find the second segment of the garland. We have two paths from the first segment, and we would like to extend those two corresponding assignments simultaneously. And we wouldn't like to refute something, to falsify some clause, because then our formula instantly becomes very easy to refute. So now we need to extend those two assignments in a nice way, simultaneously. Can we do that? Well, actually we can if they have some nice properties. Suppose both of our assignments, for every vertex, it is true that they either strongly satisfied, that means we satisfy this vertex with margin, or they do not touch a vertex, almost do not touch it, like assign very few edges. Okay, so now take a look at the vertex V, which is strongly satisfied in both of these assignments, and take a look at this bottom picture. If the values of these assignments on some edges are consistent, well, this is good, we keep it this way. And if some values are not consistent, let us just put question marks on the non-consistent values. Well, it turns out that we do not actually care what do they put in the place of those question marks, because we still have a lot of consistent ones here, and the constraint in the vertex V will be satisfied regardless of what we put in the place of question marks. So we just don't care about those non-consistent values. Okay. So we found a garland. And now I would like to say that to distinguish all paths from this garland, our branching program needs more than k repetitions, more than it has. So let us pick two paths it cannot distinguish. Now I would like to say that a correct branching program really should distinguish those paths, that I can make them have different answers in the end. Okay, so one of these paths already satisfies some carefully picked set of clauses T, and to pick this set of clauses, we use formula properties and we use the amplification trick. So now I would like to extend the other path in such a way that it falsifies only clauses from this set T. Then our paths would have different answers, one from T, the other definitely not from T. This is a contradiction for a correct branching program, and that is what we wanted. That would finish the proof. So how do I extend the assignment such that it falsifies only clauses from T? From the construction of garland, we already have some strongly satisfied vertices, and now let us notice that every assignment to variables of our formula, it corresponds to a flow in the graph. Okay, so they have those strongly satisfied vertices, and they have a lot of outgoing flow from them. Also, they have those clauses from T, and the fact that they are falsified means that the corresponding vertices have negative balance of the flow. So those vertices would be sinks in our graph. So now we have sources, we have sinks, and we just need to assign flow to other vertices in such a way that everything else is balanced. Basically, we just need to direct the flow from sources to sinks. And we can reduce this problem to a problem of maximal flow in the graph. So if we can balance our flow, then in some similar graph, max flow is big enough. Okay, so now instead of maximal flow, we would like to lower bound minimal cut. While our graph is an expander, it doesn't really have small cuts. Here, we use algebraic expander properties and combinatorial expander properties. So we lower bound minimal cut here, and that finishes our proof. In the end of my talk, I would like to suggest some open questions. For example, it would be interesting to know what happens when k in 1 plus kbps is like n to the epsilon. And it could also be interesting to consider read-twice branching programs, or to try and prove lower bound for 1 plus kbps on some more natural examples. First, it would be nice to get rid of the amplification trick to find some formulas which are hard by itself without this simplification. And maybe a suitable candidate for that would be random formulas, for example. Okay, so that is all. Thank you all for coming to my talk.